Well, welcome back to Sanford Flip Math. This is AP Calculus. This is section 3.4, which is applications of derivatives. We are deep in the throes again of the derivative chapter in Finney, Demana, Waits, Kennedy, the third edition. And thank you to them for having this lovely book. And this is just us teaching how to do some of this stuff. And here and there I'm grabbing examples out of the book. This is the example you see on the screen right now is on page 136, and obviously it's about particle motion, kind of similar to the one that we did last time we were here, which was this one, and we were talking about a particle moving on a number line. Well, this is again a particle moving on a number line. It says particle P moves on a number line shown in part A, so they're doing a little picture of how it runs back and forth. Here they're telling you that the distances are in centimeters, and it says part B shows the position as a function of time. So instead of giving us an equation this time, we get a time and position given by this graph. So for instance, at t equals 1 second, the position is 2. Okay, so I don't know what the numbering scheme would be on this line, but 1 second in, if this is something like this, 1 second in is right here. Okay, and then it stays there until the second, and then by the time so please note, it's not moving here because the position is staying 2 for that little section there, for that whole second. So starts out at 0. Okay, so watch this. This to me is, interpreting these kind of graphs is a big deal. Okay, so roll with me. At time 0, we're at position 0. Over the next second, we go, so at 1, by the time we're done with 1 second, we're at 2. So here we go. We go 1 second, and then we stay there for a second, and then from the second to the third second, we're going to go all the way to the other side to -2, and we're going to stay there for 2 seconds, and then we're going to go even farther to the left to -4. So reading this graph is a big deal. Okay, so now I'm probably giving away the whole question thing here, but okay, so starts out at 0, takes 1 second to get to 2. Okay, so 1 second, 2 seconds, then for the third second I got to get back to -2, stay there for 4th second, 5th second, 6th second, now I'm at -4. That's it. That's the whole exciting thing right there. Okay, so I know that was, just need to rewind and watch it a bunch of times. Okay, it says, when is P moving to the left? When is P moving to the right? When is P standing still? That's part A in the question that's in the book. When is it? So these are all when. When is it moving right? When is it moving left? When is it still? Okay, so tell me about velocity when it's moving to the right. Well, if it's moving to the right, it's got to be moving toward positive numbers, which means it needs to have a positive slope. In other words, increasing. Okay, so where is this graph increasing? Well, it's really only moving to the right here. It's only increase. If the slope is increasing, that's when it's moving to the right. So at this point, all we have to say, when is it moving to the right? Well, over that first second. So from time equals 0 until we get to time equals 1, it's moving to the right. Okay, when is it moving to the left? Well, it's moving to the left anytime where the slope is negative now. Okay, so this would be where slope is negative, or in other words, decreasing. Well, it's decreasing between 2 and 3. It's decreasing between 5 and 6. So from 2 to 3, and between 5 and 6. Okay. And when is it standing still? Well, it's standing still when the position isn't changing. So those 2 times. Okay, so from 1 to 2. Okay, so, sorry, let me stop here. It's still when the slope is negative. Okay, so that's happening between times 1 and 2, and also between times 3 and 5. Now, there's one little blip here that needs to be just kind of mentioned. Okay, and what that is there is a spot on here for a split second where we switch from, no, you know what, I'm going to talk myself out of it. Nope, not going to do it. I was picturing in terms of this being a derivative graph. So let me take all that back. And that was me rewinding. Okay, all right, well, we're done with that. All right, so what I'd like to do now is I want to revisit that problem again, but I want to change something. And so this is no longer number 10. I'll call it something clever like 10.5. And what I'm going to do is change this to the velocity. Okay, so this is now the velocity as a function of time. And so this is more like what you see in the book as number 11. It's more like number 18. So you're looking at a graph of velocity now. Okay, so your mindset has to change. Now, first of all, if we were talking about, now we're still talking about something going back and forth on a line, and all I'm saying now is the velocity is the graph that we're looking at. Okay, so that means that there was some kind of a position thing here. But remember, S prime is what the velocity is. So in effect, the graph that we're looking at here is now a graph of derivative. Okay, so if I start asking those same questions that I was just asking, it's handled differently. Okay, so like part A from number 10 originally asked, when is it moving to the left, when is it moving right, and when is it still, when is it not moving. Okay, all right, so need to think in terms of what does that mean for velocity. Okay, so moving to the left for velocity is going to mean, again, a negative velocity. Well, if this is a graph of velocity, then anywhere the y values on the graph, anywhere the y values on the graph are negative, are going to be negative velocity. So all of this spot right here, so this means, like for this little section here from 3 to 5, the velocity is actually -2 that entire time. So that means it's actually moving to the left at -2 centimeters per second that entire time for the time frame from 3 to 5. And then this means the velocity is becoming more and more negative, so it's still going to the left, but faster. Up here, it's going to the left slowly. Okay? All right, so again, negative velocity, if this graph is all now about velocity, negative velocity means it's moving to the left. So the question again is, okay, where is the velocity negative? Bam, bam, bam. Well, it starts at about 2.5. So from time is 2.5 until the time is, well, I guess that'd be 6. Okay? So if this graph is about velocity, the velocities are negative. On this graph, velocities are negative under the under the x-axis, okay, or the v-axis in this case. When is it moving to the right? Well, when we have positive velocity. Well, where do you find that? I guess that'd be above the x-axis, okay, or t-axis, as it were. Sorry, I got to get my colors to coordinate better. Okay, so that's all of this. Okay, so if this is a graph of velocity, then from 1 second to 2 seconds, it's moving at 2 centimeters per second to the right. The speed was increasing. The speed was decreasing. So like my speedometer, so I have my little speedometer for my little particle, and here's 0. Well, for that first second, it went up. And then it stayed at that same speed for a while, and then as we got to 2.5 seconds, I went slowing back down again. Okay, so the issue is understanding what the graph is showing us. All right, so where is it positive? The velocity is positive between 0 and 2.5. Okay, so when is it standing still? Well, it's standing still when the velocity is 0. Well, velocities are 0 on this graph on the x-axis, or on the t-axis. Well, what were those times? Well, at time equals 0, okay, so for a split second before it started moving, it was going 0 centimeters per second. And then when it just hit, so it's going forward faster, 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 faster. It's staying at the same speed. Then it starts slowing down, slowing down, slowing down. Stop. Okay, let's go backwards. Let's go backwards. Speeding up backwards, staying at the same speed backwards, faster backwards, backwards, faster, faster. Okay, so at these two spots, the velocity was 0, so it's not going anywhere. Okay? All right, so the issue is, what are you looking at a graph of? Okay, so we just use this problem, this information to do two different problems. And again, this says velocity now. Okay, this was about position. Okay, the slope of position, when the slope of the position is positive, then we're going to the right. When the slope of the position is negative, then we're going to the left, Okay, when we're not changing position, then we're still. We're not moving at all. But that's because this sucker was all about position. Okay, if I go back to velocity, these are positive velocities moving to the right. These are negative velocities. We're moving to the left. Stopped when the velocity is 0. Okay, so this graph is like a graph of your speedometer. This graph is like a graph of your odometer. How far away are you? Your GPS or your MapQuest or something like that. Okay. Okay, one other idea that I want to talk about, and there are a couple of economics, or economics if you prefer, applications that are dealt with in this section, and it has to do with marginal cost and marginal revenue. The basic idea of marginal revenue is it's kind of like a revenue per item idea. So it's a rate of change of revenue as the number of items change. The other idea of marginal cost is the revenue, is how does the cost change as the number of items change. And so they're the same idea, and the short version is that it's basically, you guessed it, derivative, and we saw them kind of pop up here, there. Okay, so marginal cost is the rate of change in cost per item. And so notice it's this clever, very detailed formula. Okay, just, do the derivative. So this is the derivative of cost with respect to the number of items. Okay, so this is basically saying, how does cost change as you change the number of items that you produce or sell or whatever. Marginal revenue, same idea, is again the rate of change of revenue as the number of items change. So the number of items you sell, produce, whatever. Hopefully that's fine. Okay. So again, do derivative. Okay, so there's nothing real deep about that, and what you would have to have is an equation for the revenue or an equation for the cost to do the derivative of. Okay, well, let's pop down to this little note here. Okay, so this is borrowed from, again, our calc book, Finney, Demana, Waits, Kennedy, and this is number 28. This is from page 138. Thank you again to authors. And so to set the stage, it just says, suppose the weekly revenue in dollars from selling X custom-made office desks is that equation. They're asking us to draw a graph. I'm not going to do that here. But then keep in mind it says what values of X make sense. Now if we're talking about numbers of desks, it would not make sense to talk about negative numbers of desks. We're not going to make -5 desks this week because we fell behind and we owe somebody. We're not going to make -1 desks. 0 desks will make us 0 revenue, which actually kind of works in this equation. If you put a 0 in for x, this is going to be 1 minus 1. So, you know, and then end up being 0 times 2,000. So, all right, so how does the revenue change as the number of desks change? So draw a graph, did that. Well, we addressed that. Marginal revenue when x desks are sold. Again, the marginal revenue is dr dx. So in other words, r prime. We're just doing derivative again. Okay. All right, well, when I'm doing derivative, I can just treat a constant multiplier separately and just do the derivative and then just multiply it. Now that only works if it's a constant multiplier. If this would have said 2000x here, I'd be kicking out the product rule. I'm not, so we're not doing any of that, okay? All right, so all we have to do now is the derivative of what's inside here. Well, the derivative of 1 is 0. So we're left with doing the derivative of -1 over x plus 1. Well, this is going to be yeehaw, a lot of fun. Okay, so I'm just going to call this y for a second. And the problem is this is not a polynomial. I can't go term by term on the top and say the derivative of the top is 0 and the derivative of the bottom is 1 plus 0 and therefore the whole thing is 0. That's not correct. I have a quotient here or a ratio here. Now there is something that we'll learn in a couple sections that will make this specific one actually pretty easy, but for now it's not. It's a quotient. So here we go. The quotient rule says the denominator times the derivative of the numerator. I'm going to grab that negative with that 1 and call that the numerator. The derivative of -1 is 0. That's nice. I like that. Minus the numerator times the derivative of the denominator. That's not so bad. Over the denominator squared. Yeah, this really isn't so bad. Okay, so this whole first term of the numerator is nothing, and this becomes minus a -1, so plus 1. So the numerator is just 1, and the denominator is x plus 1 squared. Well, that's it. You can multiply that x plus 1 squared out if you prefer, but honestly, there's really no reason to do that. Okay. So now part B again said find the marginal revenue when x desks are sold. That's for when x desks are sold. X desks. Part C, use the function r prime to estimate the increase in revenue that will result from increasing sales from 5 desks a week to 6 desks a week. Okay. Well, going from x equals 5 to x equals 6. So that is, we can approximate that. We can approximate that by just putting in 5, because what this is about is as we increase the number of items by 1, this tells us how much the change, sorry, I'm being redundant here in what I'm writing. This tells us what the change in revenue is. That's what rate of change is in this case. Okay, so all I'm going to do is take that 5 and stick it in there. Okay, so this is going to give me an estimate of how much the revenue changes when we go from 5 to 6. So that 6 is kind of implied by the little plus 1 in there and all this kind of stuff. So r prime of 5 is what we're going to find. So 2,000 times 1 over 5 plus 1 squared. So this ends up 2,000 over 36. And I don't know what that number is. $55-ish. Okay, and that's it. Okay, and it says find the limit as r prime of r prime as x goes to infinity. Okay, so That'd be the last part. As x goes to infinity, x plus 1 squared goes to infinity. This whole fraction goes to 0. So that means as x approaches infinity, our prime is going to approach 0 times 2,000, or 0. Okay? All right, well, we're going to leave it at that. Okay, so rate of change, we can talk about rate of change of position, velocity. Rate of change of velocity is acceleration. Rate of change of revenue or cost, also known as marginal revenue or marginal cost, derivative. Okay? All right, there are more applications of derivative that we will deal with, more techniques in how to find things, but many of those will happen in Chapter 4. Okay? All right, see you next time.